All right, hello class. Thank you so much for joining me again today. So, as you remember, in last lecture, we talked about how to make optimal choices, right? First, we identified what options are feasible given our budget constraint, and then we thought through what needs to be true mathematically to identify a particular option as our best choice, given our preferences. What we're going to do today is going to expand on that by thinking about several different types of preferences a person can have. Now, the reason we want to do that, the reason it's useful to have a bunch of different functional forms for preferences in our toolbox, is for a couple reasons. The first reason is, in the real world, different goods are related to each other in different ways, right? So if we wanted to talk about your preferences between Chevron oil or Shell oil, it might make sense to use a different kind of functional form than if we wanted to talk about your preferences for right shoes versus left shoes, right? Or for avocado toast versus ramen, or for food versus housing. And so if we've got a lot of different options, a lot of different functional forms to choose from, we're going to have a better chance of describing the real world in an interesting and accurate way. And it's also going to mean when we start building out from consumer theory later, we're going to be able to think about how things like demand curves or cross-price elasticities or, et cetera, income and substitution effects are going to operate differently for different types of choices. So that's the first thing, right? And so from that perspective, the first goal of today is to get you familiar enough with these 4 types of preferences we're going to be using so that you know how to solve problems. But the second goal, which I think is actually equally important, if not more important, is to help build these connections between what we're saying qualitatively, right? What we're saying in words about different kinds of choices and different kinds of preferences, and what we're saying mathematically. So the other really important goal here is to connect our ideas about the choices we're describing with the math we're using to describe those ideas, and for it to be clear to you why we're modeling the way that we're modeling. Okay, awesome. One last thing I want to say before I get right into this is that today is going to be a relatively math-intensive lecture. And so it might be a good idea, even more so than usual, to work along with me as I'm going through this rather than just listening, but also maybe to stop after each video and make sure that you're able to solve the problems that I'm describing. This is going to be a lot more work than you might want to do right now, but understanding this well and learning this well is going to be very helpful for you, both in the short term for the problem sets you're working on right now, but also in the long term of this class. Okay, so the first kind of preferences I want to start with are called Cobb-Douglas preferences. And these are really the preferences that we've worked with for the most part so far. The reason that they're used a lot is because they're nice, moderate, generic preferences that give us generally good-looking indifference curves that don't make wild and crazy assumptions. So the generic functional form for Cobb-Douglas preferences is the utility of 2 goods, x and y, is equal to x to the alpha or a times y to the b, where x and y are goods, and a and b are numbers, or if you prefer, constants. Cool. Okay, so as I've said, so what do these preferences look like? Well, let's take the simplest example, right, where a and b equal 1. So that we just have u of xy equals x times y. And let's look at one particular indifference curve. Let's take the indifference curve where the utility equals 0. Indifference curve, xy equals, the utility equals 16. So I have the indifference curve where x times y equals 16. And let's think about what this looks like. So to do this, we can think about all the combinations of x and y that'll get us to a utility of 16. Do this with x equals 1 and y equals 16. Right, x equals 2, y equals 8. X equals 4 and y equals 4. X equals 8, y equals 2. And x equals 16, and y equals 1. Right, so if we wanted to graph this thing, say from 16 to 16, 8, 4, 4, 2 and 2, 1 and 1, right? Something like this. We would say, okay, we're going to have an indifference curve here, where x is 1 and y is 16. Here, where x is 2 and y is 8, right? Where x is 8 and y is 2, right? And then where x is 4 and y is 4. So if we draw this indifference curve, it's going to look something like this, right? Yeah, that looks decent. So this is going to be this nice curvy shape that we're used to, right? The slope is going to be really steep when we've got very little x and a lot of y. It's going to be very flat where we've got very little y and a lot of x. So two things I want you to notice about the shape. So the first, which I just pointed out, is that more is better. Downward sloping. And diversity is better. Right? Slope is steeper when x is small, flatter when x is big. And the other thing I want you to notice, and this is going to be really important for how to solve this thing, is that the indifference curves never touch the edge, never touch the axes. What do I mean by this? I mean that as x gets bigger and bigger and bigger, y gets smaller and smaller and smaller, but it never quite gets to 0, right? And the reason for this is because x to the a times y to the b, right, which is our utility function, is going to equal 0 if x equals 0 or y equals 0, right? But it'll be greater than 0 if both of the two are positive. So what this means is I'm never going to be better off by giving up my last little bit of y for more x, no matter how much x I get, right? Because if I had y equals 0, x equals 100 million, I've got a utility of 0. Whereas if I've got y equals 1,000, right, if x equals 3, I'm going to have a higher utility, right? So this is going to be really important, right? Our indifference curves never touch the edge, no matter how close they get, even though the slopes get flatter and flatter, steeper and steeper. So essentially it's going to approach a limit of 0, the slope, as we go out towards x, approach a limit of infinity as we increase y. Cool. Okay, so the next thing I want to think about is what the marginal rate of substitution is going to be, right? How much y we're going to be willing to give up for x when we have Cobb-Douglas preferences. So let's find our MRS. RS, right, of y for x, evaluated at some particular xy. Okay, so what's our MRS going to be? We're going to have our MRS equal to the partial derivative of the utility with respect to x, right, the marginal utility of x, over the marginal utility of y. So let's solve each of these partials. So du dx is going to equal, right, we're going to treat y as a constant. So it's just the derivative of x to the a times some constant. So that'll be a x to the a minus 1 times y to the b. And du dy, right, we're going to treat x as a constant. So it'll just be x to the a times b y to the b minus 1, right, for exactly the same reason. So as a result, our MRS, right, du dx over du dy, is going to be ax to the a minus 1 times y to the b over, I'm going to bring the b over, b x to the a times y to the b minus 1. Cool. Okay. So x to the a over x to the a, those two cancel, right? Y to the b over y to the b, those two cancel. So this is just going to be a over b times x to the negative 1 over y to the negative 1. So our MRS is going to be, right, x to the negative 1 is 1 over x, y to the negative 1 is 1 over y, so this is just going to be a over b times y over x. Okay. Does this thing make sense? Let's think about what it's saying. So the first thing that this is saying, right, that our MRS equals A over B times Y over X is amount of Y you would give for X, which is what the MRS tells us, right, is going to be higher when A is higher and B is lower, right, when A over B is bigger. And this makes sense, right, because A is the coefficient on X, B is the coefficient on Y. So if we've got X squared times Y, or X to the 100th times Y, that means effectively that we care more about X than we care about Y. So at any given amount of X and Y, we're going to be more willing to give up Y to get X. So that's what this A over B part means. How about the Y over X part? This is the first. The second thing is higher when Y is higher and X is lower. So this is really just saying more is better, right? It's saying that if we've got more Y, then we're going to be willing to give up more Y to get X. If we've got more X, we're going to be less willing to give up more Y to get X. And the last thing I want you to note with both of these two properties is that all that matters is the ratio. So if I get really, really rich, I increase Y and X by the same proportion, right? I have 100 times as much of both. It doesn't change my MRS one bit. And likewise, right, if instead of X times Y, I had X to the 100,000 times Y to the 100,000, I would have exactly the same MRS, right? So all that matters is the ratio of A to B, the ratio of Y to X. Okay, so now that we've got our MRS, let's think about how to solve problems when we have Cobb-Douglas preferences. So the first thing I want you to notice is, if we want to think about, should we expect interior solutions or corner solutions, with Cobb-Douglas preferences, we never have to worry about corner solutions when we have true Cobb-Douglas preferences. And the reason for that is because of the fact that our indifference curves never touch the edges. So no matter what budget constraint I draw, right, if I drew a budget constraint like this, it's never going to be the case that your optimal choice is going to occur where you've got all Y and no X, or you've got all X and no Y, right? That can never happen because both of those options are going to give us zero utility. So to solve, we only need to worry about interior solutions. Which is pretty nice. So if we're going to try to solve for an interior solution, right, we laid out a procedure before, which is first we find our MRS, which we already did, right? We set our MRS equal to the price ratio. And then finally, we plug the results there into our budget constraint. So let's think about a generic problem, right? So we've got, as we had before, right, u of xy equals x to the a times y to the b. And we want to maximize that, subject to price of x times the amount of x plus the price of y times the amount of y has to be less than or equal to our income, right? Completely generic budget constraint. Okay, so we've already done step one, right? So let's go to step two. So we're going to say A over B, step two, A over B times Y over X, right? It has to equal our price ratio, PX over PY. Just to remind ourselves why this is, right? PX over PY is the amount of Y I have to give up to get another unit of X. My MRS is the amount of Y that I'm willing to give up to get another unit of X. Cool. Okay, so we can solve for one variable in terms of the other. I'll solve for Y. So I'll say Y equals B over A times PX over PY times X. Awesome. Good. Now what do? Now we know the ratio of X to Y, right? And again, let's take a moment to make sure this makes sense. We're saying that I'm going to have more Y relative to X if I care more about Y relative to X, makes sense. And I'm going to have more Y relative to X if the price of X is low the price of X is high and the price of Y is low, right? If Y is cheaper and better, I'm gonna get more of it. Cool. Okay, so now we're gonna plug this into our budget constraint, right? So we're gonna say Px times X plus Py times Y has to equal our income I, right? And we're gonna plug in our value for Y, so we'll say Px times X plus Py times B over A times Px over Py times X equals I, right? Py over Py cancels out. And I'm going to rewrite this as B over B. So I'll say B over B times Px times X plus B over A times Px times X equals I, right? In other words, oh gosh, sorry, this should be A over A. I'm losing it here. A over A, right? So this is going to tell me that A plus B over A times Px times X equals I. X is going to equal A over A plus B times I over Px. Awesome. And then we can get Y, right? By going back to this, we say Y equals B over A times Px over Py times X, which means that it's B over A Px over Py times A over A plus B times I over Px, right? Very convenient. Our Px is cancel, our A's cancel, and we're going to say Y equals B over A plus B times I over Py, right? So some good symmetry here, right? X equals A over A plus B times I over Py. Y equals B over A plus B times I over Py. Good for that. If there wasn't symmetry, we'd know there was a problem because it shouldn't matter which one we solve for first. Okay, so what this means, right, is that our optimal choice of X and Y is going to be given by this here. Great, right? Given by this here. So how do we interpret X and Y here? Well, there's a couple things I want you to notice. So the first thing is, this solution implies that we're spending a fixed share of our income on each good, on goods X and goods Y. Of income on each good. What do I mean by that? I mean that if we thought about Px times X, right, and Py times Y as our spending on X and our spending on Y, we're always spending A over A plus B of our income on X and B over A plus B on our income on Y. So these are really great preferences for describing products where that's true. The classic example, although this is becoming less true over time, is housing, where people, high-income people and low-income people, on average spend about a third of their income on housing. Okay, so that's the first thing to notice. This also has a couple of implications. So the second, if income doubles, X and Y both double. This is actually saying that the income elasticity for X and Y, when you have Cobb-Douglas preferences, are both equal to 1. You showed this on your first problem set, although we didn't have the language of talking about Cobb-Douglas preferences yet. Another thing you showed on your problem set, part 3, is that if P of X doubles, X halves, and of course the equivalent is true for Y as well. Right, we can see if we have twice the price, we'll have half the consumption of X. This is to say that the price elasticity for both goods, the own price elasticity, is going to equal -1. And then the last thing I want you to notice is that my consumption of X doesn't depend at all on the price of Y, and vice versa, right? My consumption of Y doesn't depend at all on the price of X. The reason for that, right, is I'm spending my, if we think about housing and all other goods, right? If I'm spending a third of my income on housing, if food and healthcare and all this other stuff gets more expensive, I'm still spending a third of my income on housing. It hasn't affected the size of house that I'm going to buy at all, right? So px doesn't affect y. And vice versa. Which we can also think of as having a cross-price elasticity of 0. Okay, so, all right, great. So just two more things I want to say before we can move on from Cobb-Douglas preferences. So the first is that in addition to this form, right, x to the a times y to the b, there's a second form of Cobb-Douglas preferences that say exactly the same thing, but can be a little bit easier to work with mathematically, and that I'll occasionally want to use. The way this works is, as you remember, right, all that utility functions do is it tells us whether one set of goods is better than another set, right? Whether x1 and y1 is better or worse than x2 and y2. The actual numbers don't matter. Now, it so happens that as a result of that, if we know that if some number a is greater than some number b, then the log of a is also going to be greater than the log of b. So we can define some u tilde of xy as the natural log of x to the a times y to the b. And this is going to end up, because of log rules, being equal to natural log of x to the a plus the natural log of y to the b, which is the same as a times the natural log of x plus b times the natural log of y. Now, why is this useful? Right, and u tilde of x and y conveys exactly the same information, represents exactly the same preferences as u of x and y. So why do we want to do this? Really just because taking derivatives of this function is really, really convenient, right? So we can say du tilde dx is just going to be a over x, du tilde dy is just going to be b over y. Oh my goodness, that means our MRS, as we found before, is just going to be a over x divided by b over y, which is going to be a over b times y over x. So we get to the same place as we got to before, but without having to worry about power rules, without having to do as much algebra. Okay, cool. So this is a nice thing to have in your back pocket. When you see a utility function like this, know that it's exactly the same thing as our normal Cobb-Douglas utility function. One last thing that can be useful to do is sometimes we want preferences that look like Cobb-Douglas, but are a little bit tweaked, are Cobb-Douglas with a twist. So one of the most important examples of this is when development economists think about very, very low income people, they often want to have preferences that look kind of like Cobb-Douglas, except recognizing that if our two goods are food and everything else, right, so if we say x is food per year and y is other goods, it might be the case that the amount of food per year you eat, where your utility is effectively 0, is going to be a lot lower than 0, or a lot more than 0, right? You can eat food well beyond eating absolutely nothing over the course of the year and still starve to death. In other words, there's some subsistence level of food. Which I'll call k. So how are we going to build this into our function? Well, essentially what we'll say is we'll say that our utility function with respect to x and y is going to be x minus k to the a times y to the b. And what this does, what this x minus k does, is it means that we're going to hit 0 utility if we have x equal or less than k. Right? So when we draw our indifference curves, instead of having them approach a limit at 0, they'll approach that limit at k. Right? So we'll have an indifference curve that looks like this. It's basically just shifted out by k to represent the fact that you start being willing to give up really anything else to get a little bit more food as you approach the limit at which a human can't survive. Now there's another version of this tweak that goes in the opposite direction, when maybe we don't believe that you need either good to survive. So let's say that we had X is concerts per year, and Y is movies per year. Right? We don't really believe that your utility is 0 if you get to see 5 concerts this year but didn't go to the movies, or if you get to see 5 movies this year and didn't go to any concerts. So what we'll do is we'll write a utility function that looks like u of x and y equals, let's say, x plus k to the a times y plus, let's say, j to the b. And the reason that we'll do this is now when you have x equal to 0, you don't have utility equal to 0 anymore, right? You have utility equal to k times this. So the higher k and j get, the less necessary either of the two goods are. Effectively, when we draw our preferences, we're going to have, let's say I call this negative k, and I call this negative j. Right? We're going to have indifference curves that approach limits outside of the realm of our actual plane of existence, right? So that the preferences we have left over do have corners, and corner solutions are possible. Okay, so that's all I'm going to say about Cobb-Douglas. I know this video has been long. In the next couple videos, I'm going to talk about perfect substitutes, perfect complements, and then what I'm going to call quasi-linear practice.